Well, welcome to the fall seminar series. It's titled Horticulture Innovators. As you know, we are the future of the world's food supply. Does anybody disagree? Okay, great. I thought so. And so we wanted to bring in speakers who are really expanding the horizons and bringing other ideas to horticulture, because this is the melting pot of technologies and also sustainable future. So rather than bring people from all over the world, we wanted to look inwards and see what are our colleagues doing. And several of us are really engaged in some very creative research. The simple criteria was who received some grants recently, because that is a great criteria, national criteria of finding what is competitive, right? I mean, National Science Foundation, USDA, they're the ones are really evaluating the grants. So I think that's a pretty solid criteria. So we wanted to open the series with Dr. Cisneros here. But before I introduce him, I do want to say that there is a reception after the seminar, and we have something very special that we are offering. There will be you can taste some Texas wine for that as well. So just want to make sure that, wine brings people together. It's a 1,000-year-old formula, thousands of years formula. So I'm just trying to utilize that. And thanks to all our Spirited Learning featured wineries, they've gifted us enough wine so we can do these things. I just wanted to say, so a brief introduction and I'll get out of the way. Dr. Cisneros-Zevallos graduated as a food engineer from National Agrarian University, La Molina in Lima, Peru in '88. I was only 18 at that time. That's how you start counting, right? He received his master's and doctorate degrees in food science from the University of California, Davis, and since 1998, he has been a professor here at Texas A&M University. And he's, of course, a faculty here, and he leads a program in plant bioactives and bioprocessing research. So welcome, Dr. Cisneros. We're eager to hear your creative work.
Thank you so much. So, thank you. Can you hear me? Yes. Well, first of all, thank you for considering this invitation. I mean, for me, it's an honor to start this series of seminars. And Amit asked me to give this talk about this area about the use of nanotechnology in horticulture. I've given this talk, you can imagine, many times in different parts of the world, but I never gave it here, I think. And the reason is that I do work in different areas, as you might know, plant stresses, nutraceuticals, they're very different to this. But I'm a very curious person, so I always decided to work in different fields. So when I get tired here, I go here, and then here, and go here, and it makes me motivated throughout the years. So this one's one that I really like a lot. It's about the use of nanotechnology and trying to preserve or ensure the food safety of fresh fruits and vegetables. It started a few years ago, but it was possible through the collaboration with some colleagues that I have here at Texas A&M, especially friends like Mustafa Agbulut at chemical engineering, or Matt Taylor and Alejandro Castillo in microbiology. We formed a team, and by doing this interdisciplinary kind of work, we were able to resolve what I believe is going to be a before and after in horticulture. So let me see if I can convince you about this. So the points I'm going to try to cover today is talk a little bit about nanotechnology. So most of you might know it, some of you might not. So I'll give you a little bit insight about it. Some basic principles and some examples. The use of nanotechnology under pre- and post-harvest events or conditions. And some of the research that we have been doing here at Texas A&M to illustrate some of these ideas, and some final comments. So I found this definition, which is a general definition, but will bring us into the notion of what nanotechnology is. And it says it's focused on the characterization, fabrication, manipulation of biological, non-biological structures smaller than 100 nanometers, okay? And these structures at this scale have been shown to have unique and novel functional properties. What does this mean? This means that at this level, gravity forces are not that important. And what are important are the intermolecular forces between molecules. We're talking about van der Waals forces, hydrogen bonds, dipole interactions. They're weak by themselves, but when you get at that scale, they're very, very strong, and they're capable of creating new structures, new functions that we see them actually on a daily basis. I'm going to give you some examples with this. But to give you an idea about the dimensions of what we're talking about, here we have a comparison of a tennis ball that's 100 million nanometers. And when we talk about structures of 100 nanometers, we're talking about a virus. So you can see the scale of comparison between at what level we're talking of the use of these forces that basically overcome gravity. Now, I like to always put this slide because it gives us an idea that we are able to see these effects, these kind of forces, but sometimes we take it for granted, although we shouldn't because we're scientists, right? So we're always curious and paying attention to details. I'm assuming. So, for example, when we see a lizard walking on the wall, our reaction is just to see it, and then we turn our heads and we don't pay attention to it. But we never question why is it that the lizard doesn't fall. And the reason why it doesn't fall is because at this level, there are hydrogen bonds being connecting the feet, the toes of that animal to the wall, and doesn't allow it to slip. It's very important at that level. So gravity force is pulling it, but these forces are so tiny, but so many that they overcome that effect. Another example is, for example, when we are washing plates, at home, and they become wet, and we put them one on top of the other. Have you noticed that sometimes you can actually lift one plate and there's another one sticking next to it, and then you try to pull them, it's so difficult? Well, that water in between those two plates is forming hydrogen bonds. They're bridging between those two plates, and each hydrogen bond is very weak. But when you add them up, millions of them, they're so strong that they overcome gravity forces. So these little details gives us an insight of what can be happening at a nano scale. So I'm going to give you some ideas that we have been exploring in the past few years. I'm going to give you two examples: food safety and integrated pest management. These two areas where I feel this is where nanotechnology has the big potential. So let's start with food safety. So as you know, when we talk about horticultural products, we eat everything, right? In the plant, we eat leaves, flowers, fruit, seeds, stems, roots, depending on obviously on the species, but we eat these things. And when we consume these things, we know that each of these products brings a risk, some risk of contamination. Perhaps we don't think too much about it, but when we start seeing the news that there's outbreaks, then we start paying attention. Oh, spitch contamination, where did it come from? So we start becoming a little bit more aware of these things. But that risk that we're talking about really is dependent on many factors. But as you can see, when you start comparing side by side all these different produce that we consume, from a appearance point of view, they're very different. The surfaces, look at the roughness that you see here compared to this one, or the smoothness of this tomato compared to, say, a leafy green. They're very, very different. And we're going to try to see why I'm putting emphasis on this. So some time ago, I made this little diagram showing with electronic microscopy how that roughness actually did change for a group of different selected crops, from going from cantaloupe all the way to tomato, which you can see very smooth all the way to something more rough. When you start looking at the unique structures, you start seeing that there are crevices, there are some depressions here. In other cases, they're a little more smooth. And when you pay more attention, you start seeing that there are even lenticels here that can be hiding places for these organisms. So we were able to classify them visually into what we call high roughness and low roughness, but at the same time, there are ways from a physical point of view to determine that roughness. You can actually measure these crevices and heights and depth and things like that. But let's look into some pictures to show you where these microbes are hiding. So this is cantaloupe. So we're gonna go from here. We're gonna take, for example, some of these surfaces to show you where these microbes are hiding. So let's look for cantaloupe. You know, cantaloupe is like a mesh, right, in the surface. So there's a white area and a green area. So this corresponds to that white area, and this is the green area. And you can see that the arrow is basically pointing at this little structure, which is kind of like a fracture here in the wax layer. And this is about 1 millimeter in distance, if you want to call it that way. Then we increase the magnification to 100 micrometers. And you can see, obviously, that the structure a little bit more clear. And you can see actually the cells below it, right? And then you increase this to 10 micrometers. And this edge here corresponds to this part here. And we can see the cells behind. And when we start pointing the arrow exactly at this point, and we go to 1 micrometer, which is 1,000 nanometers, we can see the cells. They're there inside this little depression here. And believe me, if you try to put water and wash them, they're not going to come out. Because there's an air gap here that's basically protecting them. And because of the high surface tension of water, it's very, very difficult to get inside there. Okay? But to discuss an insight, this could actually explain why there has been some outbreaks in cantaloupes coming from Mexico. Because once the microbes gets on that surface, it's almost impossible to get rid of that. Strawberries. So here you have a seed, and there's obviously kind of depression around it. So we're going to point out this purple arrow here. This is 1 millimeter. We amplify it, and we go directly here to 10 micrometers. We continue with that arrow, and we see some little spots here. We amplify it, and we see the microbes inside here. Now, keep in mind that these pictures were done with us inoculating them, okay? So the question is, we put them on the surface, and these things are getting inside, okay? Now, do microbiologists know how they get inside? Nobody knows. Right now, there's not a one strong theory that could explain how microbes get inside these crevices. We have a theory, but there's another one, and I'll explain to you why the other one doesn't, I don't think it really works. But it's at this point, it's just a matter of opinions at this point. But I'll show you some more evidence about this. Curly parsley, no? So here you see this, the leaves. We increase the magnification. We start pointing out here. You see some stomatas right now at this point. We amplify it. You see another stomata here. We amplify the arrow, and we see the microorganisms inside. So they're getting inside here as well. And again, once they get inside, there's no way you can wash these things. If this is E. coli, Listeria, you will get sick. Okay. So, question is, from, you know, the advantage of being someone that's coming away from the field, because I'm not a microbiologist, but I've learned in the process, is that sometimes you bring this idea of a view that's very different to the people that are inserted in the field. And this allows you really to bring some new ideas into the field. This is what we do. So I made an assessment of what I thought, or what we saw according to the literature, where the risks were. And there's a risk of contamination, obviously, that has to do with that roughness that I just showed you and that surface chemistry. Most of these waxes are very non-polar, which means that their surface energy is very, very low. They don't tend to adhere to water. They don't tend to pull water. Water molecules like to be together. So water tends to be formed like little spheres once they touch these surfaces. And the other thing that we also observed that was not very well explained, so this part is not well explained, how this contamination takes place. And the other part that's not very well explained in the literature is, okay, once the microbes are in these crevices, how do we get rid of it? Because these air pockets, I was telling you, you can have water here trying to wash it, and you think you're washing an apple, but you're not really washing an apple. You're just getting rid of some of the soil on top, but the microbes inside those crevices, it's not going to happen. You can put surfactants, and it's not going to happen as well, because in surfactants, it works, obviously in theory, it wets the surface, but it doesn't displace the gaps of air. It's very difficult. So this is an issue too. So these are the two main aspects that we believe are the ones that are driving or putting an obstacle to come out with novel technologies. So once the contamination takes place, then there's colonization of the microorganisms. You can have biofilm formation, and that's it. That's it. Or once those microbes are within those holes and they form these, they're right in the bottom of those holes, and you have those air gaps. That's it. So we have two cases here, very difficult to overcome. Now, where are those sites, those possible sites of contamination, either in the field or in post-harvest in the packing houses? Well, in the field, you find them everywhere, basically, aerosols. So the microbes are being transported in these little spheres of water, if you want to call it, are floating in the air, or through splash if the water is contaminated, or through penetration and through the roots. However, this is very debatable because there are some groups say that microbes can actually go through the vascular tissue, and some other groups say no. I'm a little bit not sure about it because from my studies with roots, there's what they call a Casparin strip within the root, and it's very tight. And the only way you can go through that is through openings that have a nanoscale, and it's for elements, not necessarily for microorganisms. However, my colleague in Alejandro Castillo has a theory. He believes that perhaps some of these microbes can actually secrete enzymes and find their way towards those vascular tissues. So that's the reason why I'm debating about that part. And obviously the contact of, when people contact or animals contact directly some of these leaves or fruits, you don't want wild animals in the fields where you're producing these things because they can actually bring some of these microorganisms to the surfaces. For example, lizards or birds, they can actually bring salmonella to surfaces like in cantaloupes. It's an issue. We have some general agricultural practices, but it's not enough. Okay, it's not enough. We still have problems, outbreaks. And same thing happens in post-harvest. We handle these things when they comes into the packing house, so there's hand contact. The surfaces in which these products, if they're contaminated, they will contaminate the products. If the water is not treated well, or the containers are not proved to be free of microorganisms, they will contaminate the surfaces. So just think about it. I've just counted eight spots. So it's a challenge where, the people that do horticulture, our farmers all around the United States, I mean, they do a great job. But we still cannot rely on not taking care of all the different risks. So we need to come out with something. So I was telling you that there is this area. What I saw is that there was still a lot of gaps, many gaps. There's a lot of people working in this field, but they don't have this integrated vision. So they don't. This is one of the things that a lot of researchers don't do. They don't step back and they don't see the big picture of things on an integrated form. They do isolated work. And when they do that, that's when they leave those gaps to be remaining there. And that's an issue. So one of the gaps that's remaining is exactly that point where I was telling you, what's the theory? What's the possible mechanism by which contamination microbes can actually go inside those crevices? One of the theories is that when the microbes get into the surface, they have these filaments or I call structures that allow them to move. And it's true that they move, but they only move if there's a continuous layer of water. But in a surface like a leaf or a fruit, you don't have a continuous layer of water because it's a waxy material. So it's impossible for a microbe to land and start moving. That doesn't happen. But that's one of the theories that is proposed right now, and it came from Israel, if I have this correct. We propose something different. We propose this idea where whenever you have these aerosol or droplets of water landing on a surface, and because there's already crevices, when evaporation takes place and water moves, it leaves a very thin layer of water above those crevices. And there's a moment where these things collapse and they contain the microbes. And when they collapse, they get inside. So I'm going to show you with this film that we did, this idea. So you can see how the water line of the droplet is retracting due to the dehydration process. It leaves layers of water on these little holes and they disappear. They rupture, in other words, like that. You see that? And when they rupture, and so you can see here, for example, this is another view. This is the air gaps. Depending on the size of the hole, some of them are less deep, some of them are more deep. And when they rupture, when these things rupture, the liquid goes inside and it brings with it the microbes. This is our theory. This hasn't been published, but I think that when we publish, it gives us a good idea because for the first time, we have an insight of how to attack the problem. So, two things. We want to address this issue. How can we avoid contamination? That's the first one. How can we avoid this? And how can we resolve this thing about the gaps? So let's see how we can avoid microorganisms attaching to surfaces. So one of the things that I always tell my students is that what makes a good scientist from the rest of the scientists is to obviously be very curious, but to pay attention to the details. For example, this thing about the lizard walking, on the wall, we take it for granted. But us, because we're an elite group of people, compared to society, where we're here, we're training our brains all the time, we should always be trying to find an explanation to things. So there's an area called bioinspiration, where we go look at nature and we try to see what nature has been doing, and we try to bring some of that information and try to replicate them and see if we can actually use them to create new technology. So one of them is basically observing what happened in rice leaves. And we saw that they were very, very hydrophobic. They didn't allow water to get in or stay in the surface. So I requested some rice plants from Cisneros-Zevallos, and we brought them all the way here. And with my colleague and friend Mustafa, we started studying them. And what we saw was very interesting. So this is the rice leaf. You can see how the water forms a little ball here because the waxy layer has. And we can measure the contact angle. The contact angle is the angle that in the internal phase that you see here. When it's above 100, it's hydrophobic. When it's above 90, it's hydrophobic. When it's below 90, it's hydrophilic. But if you're going to something like 135, it is really very hydrophobic. And if you go to 150, it's super hydrophobic. It means that the water just rolls out from it. So we looked at what was going on there, and we saw these little cylinders of wax that was in the leaves. So this was electronic microscopy, and you can see these little deposits of wax that form little cylinders with a hole in the middle. And what we realized is that when water was touching these surfaces, basically gaps were formed of air and the water was not spreading. It was very hydrophobic. And that means that if this this droplet contain microorganisms, there's no way the microbes will basically adhere to these surfaces, okay? So we basically did that study. We inoculated microorganisms in areas where we had these, we saw these structures. In areas that did not have those structures, you can see the microbes are here in between, but they're not here because they don't have that ability. The water just rolls out, okay? So we said, okay, this is happening in nature. Why don't we replicate these things? Why don't we create surfaces that have these kind of structures? This is what we did. We took glass, quartz. It's very hydrophilic. We went through a self-masking etching process that allows the creation of these nanotextures, and it gave us these little cylinder type structures, very similar to what we saw before. And then through methylation and the use of a molecule here that allows us to basically create a very hydrophobic surface through this methylation process, allows us not only to have the etching and the formation of this nanotexture, but to basically change the chemistry. So we're changing the chemistry from being something hydrophilic to something being hydrophobic. And at the same time, with that nanostructure that I was just mentioning to you, we were able to create those air gaps in between. So we ended up with these surfaces. And if you see this surface compared to these surfaces, they look alike, very similar, okay? So they were transparent, which is very nice because it's glass. And then we put water, and guess what? We had a larger contact angle to the point that this contact angle is telling us that that surface is super hydrophobic, even better than nature, okay? So with this kind of things was the basis of our journey in this area of nanotechnology. This is the start point. And it started in a restaurant, I remember, just with a napkin and coming with all these ideas. And it was fun. We were having fun. And you can see here, for example, how this pristine quartz, which is the glass, we could actually make that glass become hydrophobic. And this is the glass that contained the nanotexture, the one that I was telling you, and hydrophobic at the same time. And you can see, for example, when we dip them in E. coli or Staphylococcus aureus, you can see that the hydrophilic surface was completely covered by microorganisms. But then when we changed the hydrophobicity or the hydrophilicity of the surface, you had pockets of microorganisms trying to stick to that surface. But whenever we try to, we encounter them with these surfaces that we created, basically there was nothing, okay? And I can show you a video that illustrates this idea. So we have a microscope here. We have our targeted surface, and we have a little chamber where we were passing these solutions that had the microorganisms. And I'm going to show you a video illustrating this idea of about attachment. So let me show you how it works. What you're going to see now is the uncoated quartz. This is just a regular glass. And we're passing these microbes, and we can see if these microbes are just passing along or they're sticking to the surface. In this case, they should stick to the surface. You can see that? They're sticking to the surface, okay? So that's the uncoated quartz. Then, this is the coated quartz, which means that we took that glass and we made it hydrophobic. Now, in this case, we should see those microbes passing by. Some will stick, and the rest will pass by. Oh, what happened here? Sorry. You see that? Okay. Now we're going to see with the material that we created, this glass that had this nanotexture and this hydrophobicity, and you will see that basically everything passes by. See that? Okay, so this is very convincing because we do have the data with microorganisms. We are able to create the surfaces. Now the question was, what can we do with this? And there were many ideas from there on, because not only we were able to create a surface that was not able to be attached by microorganisms, but it was transparent. So this is a measure of transparency of that glass. So you can actually not even tell if the glass is there. So imagine, for example, a cell phone. We modified all these things, these surfaces with this kind of material. Basically, no microbes will be contaminating here. So you can use it here, or you can use it in conveyors that are basically handling produce or a medical device. So the uses are endless. Okay. So we said, okay, I think that we kind of like understand now how they get inside here, and I think that we believe how we can avoid it by changing these surfaces and created very surfaces that have these nanotextures and that are very hydrophobic. So we are able to manipulate surfaces. So we might be able to eliminate the risk of contamination. First step. Okay, so this is good. Then comes the other big question. Okay, so we answer one question, and obviously there's a lot of things that we can still do in the first part, but let's see what we can do in the second part. And this talks about what happens if the microbes are already there. What can we do to eliminate those gaps? Because believe me, once they're inside those crevices, you cannot get rid of them. Water, superficial water is so high that it's impossible, to be driven into those holes or those crevices. So we came out with this idea. We said, okay, what if we create nanoparticles of water and we spray them on the surface, and those nanoparticles of water are going to go inside those crevices. They're going to fill those spaces, and then we submerge them in our sanitizer. We kill everything. That happened in a restaurant too. Just thinking about some of these ideas with Mustafa, and he said, let's put it in practice. And we went there, and we created these nanoparticles. We have devices, equipment to do these things. And this is the theory. So we make a cross-section of a surface that has the bacteria inside. I was explaining to you that whenever you apply water or sanitizer, this happens. There's the air gaps. It's impossible to reach them. And this is what we call the Casey-Baxter state. This is for engineers, physics. They call it the Casey-Baxter state. However, in our mind, in our idea, we said, okay, what if we create nanoparticles of water first? So we spray them. Imagine the fruits are going through a conveyor and we spray them with these nanoparticles of water. Now what's going to happen is that we're going to fill these gaps with water, and then we put them in touch with a sanitizer, and because they're already filled, then the sanitizer can diffuse and get into these and reach these microorganisms. This is what we call the Wenzel state. So we, in theory, we were coming with all these ideas, but then the big challenge is, can it really happen? So we went ahead and we, to be able to demonstrate this, we took some leaves of spinach and we made soft lithography, which means that we were able to replicate the surface using a soft material. And then we had many surfaces very, very similar to them. And we, what we did is, we did these little tests where we used fluorescein in bulk solution. So that means that we dipped these surfaces in a bulk solution, and you can see that the fluorescein doesn't get inside those crevices because I was telling you about the gaps. But then we aerosolized the fluorescein solution, so we sprayed them, and then you can see that now they fill in to the bottom of those crevices. And then what we did is we put in test our idea, our hypothesis. What happens if we spray with water first, and then we dip them in bulk fluorescein, and guess what? We had a more brilliant, fluorescence on the surface. So I said, my goodness, we got it. Let's test it now with microbes. And this is what we did. So this is a control. This is the aerosol water, just water. This is bulk hydrogen peroxide, which is the sanitizer. This is aerosol hydrogen peroxide. And this is the combination of aerosol water and H2O2. And look the decrease in the surface of microorganisms. Basically, 6-log reduction, 5-log reduction. This is big, dramatic result. Okay. So when you say, my goodness, we were able to do it. This is good. So going back to this, so we were able to demonstrate this, and we were able to basically show that the two main problems could actually be resolved. Okay. So first thing we did is send a proposal to USDA. And we got this one here. It was almost $1 million with Alejandro Castillo, Matt Taylor, Mustafa, and myself. This was a couple of years, 3 years ago, 2 years ago. We were very happy trying to look for different materials. And we published a lot in very good journals. We were exploring all kinds of materials and trying to modify them using all these concepts that we came with. And we kept publishing and learning in the process with our students. We learn from them, they learn from us. We became more adventurous to explore new materials. And then we said, I think that we are in the state to send a big proposal to specialty crops. Let's go for it. So we sent one on 2021, and we said, let's not go alone. Let's do it. Let's make this big. Let's go ahead with some friends and colleagues that we know in different states. So we formed the group: Texas, Alabama, California, Florida, Georgia, Illinois, Maryland, Mississippi, Michigan, North Carolina. And they believed in this idea. They did it. They came with us, and we got it. And we got this big grant. And this big grant, what does it mean? So this is Mustafa here, me. We're just pretending that we're working. You can see here. And what does this do? So we start aiming at different things, because whenever you get one of these grants, it has to have the fundamentals, obviously, but it has to have an impact. And I tell my students all the time, you always have to have a successful story in your projects, because that's the way to sell ideas. If you don't do this, it's very difficult to be convincing if you just stay in the fundamentals. So we said, okay, our idea here is to work on transforming many of the different tools and operations that go from the field all the way to the consumers. That means bins, gloves, anything that's in touch with the produce, directly or indirectly. And we need a very important extension component. So this is where we work with our friend Joe Masapny, and he is coordinating with many of these colleagues in different universities that I just mentioned, because there's all these other colleagues are working on the extension component to make this impact become real. And we selected per state different crops, and we selected different tools that we want to target with this project. And right now the research is ongoing, so we are collecting data as we speak here. But this is the idea. It goes back to the principles that we saw before, no? We talked about the idea of creating these nanotextures, and we have different ways of doing it. We can do something like spraying a solution and allow the assembly of those nanotextures. So in a way where we can actually renew the spray on a season basis, if we want to do that. So we can tailor the length of the duration of that coating system. We can use grass materials, so we don't have issues with FDA, for example. Or we can use, and this is on a picture of the arrangement, of the type of arrangements we can achieve. Or we can do something more permanent, where we basically, from the start, when the material is being done, we can incorporate some of these chemicals or structures that could be silicon or can be nanodiamonds, for example, to form this nano roughness, and then change its chemistry, and these materials are more durable in time. So we can play in both sides depending on what's the needs and what the farmer wants to invest. And the applications are endless. So we're in this project, we're just focusing on things related to the produce, excuse me, the materials are in contact with the produce. But another thing we want to do is, what if we actually design structures in the produce itself? It's never been done before. And we're exploring that idea as well. This is a very challenging phase, okay? And one of the advantages that we see here is that we can actually apply It's not only for getting rid of microorganisms, but also for soil, because the principles of interfacial phenomena of interaction between a material and a surface is the same for microorganisms or say soil. It's the same thing. So what does this mean? That if we have surfaces that are where soil cannot attach to it, then we can reduce the amount of water that farmers are using for washing operations. I mean, this is a big thing, a very big thing. So we're also exploring this with our friends and colleagues in Georgia. They are the ones in charge of demonstrating this part, and we just had a meeting last week about it. We're excited about this. So I'm going to move on to, it was not intended, but is it okay, Amit? Really wanted to talk about this part here. And the reason why I wanted to talk about this part here, because it's very into my heart. And the reason is because my father was an entomologist. He was, I was an empirical entomologist since I was a kid, let's put it this way. So let me tell you this little story. And the reason why, how I tied this knowledge and the possibility of using nanotechnology here. So it's called integrated pest management, because most of you know that when you're trying to control pests in the field, you use components of IPM. You use different tools to kind of like control the presence of insects to a level that doesn't have that economic impact. That's the whole definition. And you can use biological control, but you can use also biotic or abiotic measures as well. So there's a story behind this, what I'm going to tell you, and it comes all the way back to Peru. I was born here, but I was raised here. And basically what's unique about Peru, in the coast of Peru, it's a desert, even though it corresponds a tropical environment. We should have rain there. But the mountains, the Andes are so high that when the clouds are forming the Amazon bases, they don't cross the mountains, and it doesn't rain in the coast. So the coast is the desert. But it rains in the mountains. And when it rains in the mountains, the water falls like in rivers. So what's unique about it is that every 2 hours by car, it's complete desert like the moon, you find a valley. Another 2 hours, another valley, and so on. This is beautiful, actually, because these are like isolated greenhouses, you know, very nice. But what Peru did, but the miracle that happened in Peru, and this is the reason why I'm very proud of being in horticulture, is because what I learned since I was a kid is that horticulture is one of those disciplines that really creates a lot of job opportunities, okay, massive. And we've seen it in Peru. Peru, back there in 2000, had 50% poverty. And in a matter of 10 to 15 years, that poverty went down from 50% to 15% through horticulture. Mainly because they start irrigating these areas and creating massive amounts of jobs. And by doing so, Peru became the largest exporter of asparagus in the world. We never produced asparagus before, and we became the #1. And right now, I think they're the largest in blueberries. So you go to these areas, like for example, this is our fields of asparagus. It's a desert, so this is sand. You can see that everything is through drip irrigation. So they brought the rivers here, and through channels, they diverted them, and they start irrigating these areas that were basically deserts. So it's amazing for us. You know, if you have the chance to go there one day, it's amazing, because what we learn in the books, saying, you know, asparagus, you can only get one harvest. No, over there you get 2 harvests. But in the books, they tell us something about avocados. You go there, something different. So we're always learning something different due to the fact that when you manipulate water under those conditions, it challenges the concepts of horticulture. So why do I say this is dear for me? Because my father, he was called. He was very, very well known there. He was an entomologist. We're very close with Ray Smith and Ingeniero Herrera. These are the fathers of IPM. You know, now I realized that I met these people when I was a kid. So this is my father. This is my brother Pedro. This is myself here. And we were looking at in the desert, you know, things about asparagus. And he always told us, this is this is going to change the agriculture in Peru. And he was able to implement IPMs in Peru, and he transformed agriculture in Peru. So big part of what happened in Peru is thanks to him. And one of the things that I learned, I was telling you about empirical entomology, is that we were 5 brothers and we were 5 little kids. You know, my father was there and talking about entomology and plants and all these things. I mean, he brainwashed us. That's true. So that's the reason why I'm here. But the thing is that I remember when he passed away, I started reading all his books again. And I realized, my goodness, I know something. And I realized he always said, the future of IPM is in the development of components of IPM. And that stuck in my mind. And I said, okay, I'm going to do this. I'm going to bring nanotechnology into components of IPM, and I'm going to try to transform IPM. So this is my next mission. Because what happens is in IPM, the presence of, you can find different ways of using components to control insects. You can find them making organic pesticides into systemic pesticides. There's no systemic pesticides right now for organic, let's say, horticultural practices. And we were just recently, we published a paper showing that it is possible. So we can basically create from neem oil, which is an organic pesticide, we can create nanoparticles, apply them to the plant, and we have shown how these things go through the roots, and they can be distributed in the leaves, and they're just waiting there for the plant to be attacked, And or we can create, for example, systems where we can create attractants for nematodes, and in a way where they can be applied and bring the nematodes to a certain place, attractants, and then apply the nematicide or whatever is utilized to kill them. Or we can basically create, say, sticky traps or slippery traps surfaces, or come out with, I don't know, say, systems that can diffuse hormones instead of having these traditional hormone traps localized in one single place. Spray them in nanoparticles so that you can confuse the insects and they will not mate anymore. So there's many ways where really nanotechnology has the potential to innovate components of IPM and transform them. And we're just there at the tip. And this is our next step. This is what we want to do. So we want to continue using nanotechnology in food safety for sure. We're going to continue. There's more to explore there. But this is something that I feel will be the next step for us. And hopefully next time, if I get invited, I'll show you some results here. And basically, it was just some data that was showing and demonstrating how we can put nanoparticles and they would move along the vascular tissue and be localized in leaves and so on. But we've done work even beyond this, and we know where they move, how they move, and how they get into these vascular tissues. So final thoughts. I do believe that nanotechnology in horticulture is still in its infancy. There's some things out there, but just like pieces of a puzzle. I do believe that there are many factors involved in microsurface interactions, and little is known, but this kind of research using a nanotechnology approach allows us to understand many things, like the way things are contaminated. Prevention decontamination is very difficult, but I do believe that with information that I'm showing you today, and as we worked hand by hand with the people in extension, we can really make an impact. And I do believe there's going to be a before and after once these technologies go to commercial use. The research progresses. I mean, we're still working hard. I mean, we try, we think we're working hard. And we're doing fundamental studies, and we're trying to come out with these practical things. For example, today we submitted a proposal with Amit and with Mustafa and a very new concept of how to retain water in the soil using nanotechnology tools. This is a new thing. And we are different fields, you know, and we can bring all this interdisciplinary approaches. There's opportunities out there. And I think that there's potential for exploring its use in prevention contamination processes. I think that, especially for the case of food safety, and I do believe that in IPM, it will have the same effect as well. And with the thing that we proposed today, which I didn't talk too much about it, and the retention and utilization of water as well is another big thing in the future. So with this, just want to thank my good friends and colleagues, Mustafa Bulut, Alejandro Castillo, Matt Taylor, my group itself. So we're a nice team of people and students and different fields, and we like to work together. So thank you for the opportunity to be here. Thank you. Any questions? Yes.
Have you ever tried to spray a fruit or a vegetable with aerosolized peroxide? And if you have,
Yes.
how much pressure do you have to
Yes.
use? How far can you transport the particle?
Yes, you know, so it has to be nano level, not aerosolized, because it's too large and it will not get into the crevices. The issue with spraying some of these, we try to do it with hydrogen peroxide, is that because these things get charged, once they're approximating to the surface, they basically collapse and they form larger size particles. So it was not feasible. So we had to go back to the idea of using just water, and the first approach of doing the nanopriming and then the sanitizer. But we tried, but it didn't work.
So your concept is that if you keep the contaminants from building up on the equipment, then you're going to reduce the bacterial load on the product.
You have to, yes, because cross contamination, once you have microbes on the surface, let's say of a conveyor belt or something, and the fruit gets in contact with that, there will be transfer of microorganisms. That's called cross contamination. It happens, yes, and it happens not only there; it happens in the kitchen.
Yeah.
So it's a very important thing. Yes.
So I worked in Mexico many years, 51 years. And sometimes my friends would eat the wrong food and they get monitored within.
Yes, it happened to me. Yes, I know what it is.
Uncomfortable situation. You get out of the car in a hurry and not pleasant. So
Yes.
you go in a restaurant here in College Station and they wipe the table down and you can tell the way they wipe it. They're not doing a good job,
They're not.
but they're using chloride.
If they're using chloride, okay, there's two issues there.
Chloride is the main thing. we
Yes.
use
Yes,
today.
yes,
Nobody gets sick, so the current system is working pretty good.
yes. Well,
So before we adopt your system,
yes,
you know, we're doing okay the way we're, no one's gonna get sick tonight. Everybody in this room will go home and eat, and nobody's gonna get sick. That's a good system.
yes,
But you could go to a village in Mexico where if you don't take extreme precautions, you'll get very sick.
yes.
So.
And yeah, so what's your question
So
is?
the question is,
Yes,
on this nano deal,
yes.
can we get sick from that?
Not from the nano, not from the nano, but what you're saying is correct. I mean, the
My
US,
question is, are there any human diseases
yes.
that are gonna be so small that we have to worry about the current system is no longer any good? And suppose we have to go to, how are we gonna industrialize nanoculture?
No, let me tell you, for example, this thing about the nano priming. So you have a conveyor, you have to come out with technologies that will not alter too much the way they do things. So you have a conveyor with the produce moving, and then you have a system that can do the nano spray before the sanitizing process. Once you do that, and you are able to fill in those little crevices that I was talking about,
That
then you
nano
go.
spray, does it have anything in it, or is it
Just water, just water. This is what we were talking about. We tried even sanitizers, but we realized that sanitizers get charged, those particles, and when they get charged, they pulled to each other and they form, and they're not nano anymore. So they lose their ability to get into the crevices. Yes. You had a question, you know.
Kind of similar, good presentation.
Thank you, Bill.
What I was wondering is USDA, there's a big association they formed, they will put together proposals.
Yes.
The big question there is going to be, what God is asking for safety of the nano particle,
Yes.
gold or silver or whatever.
Yes.
Here.
Yes.
What about the safety of the nanomaterial itself?
Yeah, that's a very good question, and it's a very, very important question. When it comes to water, it's not an issue with the priming part, but when it comes to, for example, the coatings or the materials that we use to create these surfaces, we're very careful in using grass status material. So we're using compounds that have been proven not to be toxic of any kind. It limits our ability to do things, but at the same time, it will reduce the resistance to adopt these technologies. Yes.
When we squirt water as large particles or molecules or whatever, but you're saying we're gonna affect the water so that it's nano and it'll cover better.
Yes, it will go into those crevices, and we showed it in this
Now, is
experiment.
that gonna be with a gun of some sort?
Oh, there are ways to do it.
Just equipment?
There are equipment to do it. Yes. Yes.
Good question. It has to do with the nanoparticles themselves. You're using ones that potentially don't have toxicity, but what is their longevity? So you're gonna put them out into the environment. Now they're gonna be coating surfaces that you hadn't expected that they're gonna be coating. So, you know, it's one of those things where you have to wonder about the longevity and off target.
You mean of the nanomaterial that we're using for the coatings? Well, let's put it this way. Every molecule that we consume is at a nanoscale. So starting from there. Now, in this case, for example, these nanoparticles are nanomaterials that we're using are FDA, they're grass status, which means that they have been proven already to not have any sort of toxicity. We don't go with materials that are not grass status. Yes. So that takes care of that part, you know, in some way. Yes. 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 Ozone, yes. Ozone, yes. Okay. Compared to ozone? No, I'm glad that you mentioned this because there are other techniques. Obviously, ozone is one of them, irradiation is another one. But the problem with those techniques is the following. Ozone is an oxidizing material. So yes, it will target the microbes, it will damage membranes, the DNA, but it also will damage the cells. So you have to be very careful in the levels that you use. And sometimes it's not specific. I mean, whatever kills this, it will be damaging. In the case of radiation, it's something similar too. There's different ways of using radiation. You can use an electron beam, for example, or you can use gamma. And whenever you use these things, same thing. Usually when you want to get a food safety effect, there are certain guidelines. You want to do a 5D reduction. And to get a 5D reduction using gamma or E-beam is very difficult. You will damage the tissue. So it is a balance. And that's the reason why these techniques are not widely spread, because of these issues I mentioned. Yes.
So With the little filters, the nano filter.
Yes, the wax, yes.
Like, how efficient is efficient?
Yes,
Like, what, because I'm thinking.
Yeah.
it's called a plant bed,
yes,
then the fungal spores can get on it. And then one of the make that, like, fungal toxin.
yes.
So I don't know, like, how can, it's like, eight, five.
Yes, that's a very good question. Okay, and the truth is that we're still working on that. And just to give you an example, do you like blueberries? Okay, what's unique about a blueberry when you see it on the surface? They're kind of whitish, right? Do you know why it's white? Because of the wax. So you, if you look at the electron microscopy, you will see that it's like filaments of wax. Okay, and when they're like this, all entangled, what they do is they diffract the light. That's the reason why we see it white. Well, if you pass your finger, what happens with it? It turns purple, no? Because you're destroying that structure. So what happens that in nature, many of these wax structures are very delicate. They're not designed for us to touch them. They're not designed, for them to be protected. So the issue is that they accomplish their goal of avoiding these contaminations, but we cause the problem because they're very fragile. So our goal is, how can we reproduce something like that where the structure is enough to resist the touch or any mechanical, I don't know, movement as they go along the chain, in post-harvest handling. That's a very good question.
Well, let's thank Louis for.
Thank you, appreciate it, thank you. Thank you.
There's a.
Thank you so much, appreciate it.